We really wanted to innovate in a way so when you combine with wind and solar, you could actually be competitive and even cheaper than fossil fuel. And this really drove a lot of our innovation to come up with a combination of conventional physics technology for speed with some of the latest innovations in AI, software, and material science to create an energy storage breakthrough.
A global technological revolution is underway.
We think in the next 10 years, you'll see more innovation than we've seen in the past 50.
Driven by passionate, dedicated individuals intent on shaping a new world.
I want to create something new. I want to create something that gives me the sense of creating new life. This is why I'm here.
A greener world.
This is the last call to action, that we have to develop the solutions that are protecting our planet.
A better world.
I have a family, and when I think about the life I want them to have and their children to have, I want them to experience the world where they can travel and live without worry, and that gets me up and going every day.
Together, they are pushing engineering to its limits.
Human creativity is the most tremendous power, and if you set a target, things that you never thought possible become possible.
Creating extraordinary machines that can help the planet and humankind in the future. Engineers are transforming the way we power the world, replacing old carbon-intensive technologies with clean, renewable sources of energy. And the speed of change is unprecedented.
The energy transition that's happening at the moment is a complete paradigm shift. Rather than big, centralized thermal generation, burning coal, burning oil, burning gas, we're now decentralized, solar, PV, all over the place.
Wind and solar, which are now commonplace, really, they were almost non-existent. They were just a minority thing 20 years ago.
But the meteoric rise of renewable energy has consequences for our electricity supply. While coal and gas-fired power stations can generate electricity whenever you need it, renewables are intermittent by nature. So we need a backup plan for when the wind stops or the sun goes down.
So the solution to intermittent power provided by renewable energy is to provide power quickly using energy storage devices.
Teams of engineers are searching for ways to store green energy with mechanical batteries, so that when extra power is needed, these devices can bridge the gap instead of relying on more polluting sources of electricity.
The ultimate solution really is to have much, much more energy storage built into the grid, so that at times when there's a surplus of energy, such as when the wind's blowing very strongly and the sun is also shining, one can save energy and store it.
We're going to need a lot of innovation for new technologies to be able to store this energy so that renewable can generate and we can utilize that when the grid needs it, when the demand is.
The success of the green energy revolution depends on these engineers and their marvelous machines.
If we were to keep increasing the amount of renewables on the grid, but we didn't implement energy storage at the same time, our grids will start to get unstable. We'll start to have more and more frequently periods where power wasn't available to us.
Already, there are ominous signs of what a future might look like without enough energy storage. In August 2020, California was about to experience a glimpse of this potentially devastating future. The most extreme heat wave of recent decades was wreaking havoc on the western United States. Elliot Mainzer, CEO of the California Independent System Operator, was paying close attention to the weather.
August of 2020 saw a heating event that hadn't been seen in many, many years. It was simultaneously extremely hot in just about every part of the western United States, with temperatures well into the 100 degrees in California and in many parts of the region. It was what we've referred to as a heat dome that sat over basically the entire western United States.
Then, sweltering Californians were suddenly confronted with another rare event. From 6:30 p.m. on the 14th of August, their electricity was suddenly cut off.
It was the first time that California had experienced any types of rotating outages from a shortage of electricity in 20 years.
This shortage may seem surprising, as California has invested heavily in green energy generation. In fact, during the spring, they have so much solar power, they export it to neighboring states.
California is, first and foremost, very blessed to have a very significant solar energy resource. We've had we have over 15,000 megawatts of solar operating on the high voltage grid, and also behind the meter, a lot of rooftop solar in California.
So, with enough solar panels to power nearly every household, why did California run out of electricity during a heat wave, when there was plenty of sunshine? The answer was all in the timing. As the sun went down, power-hungry air conditioning systems stayed on, so the supply of solar power fell while demand for electricity remained high. In the evenings, California often imports surplus electricity from neighbors, but this time, they couldn't rely on other states.
It was so hot in these other areas that they needed that electricity for their own customers and didn't have as much surplus to sell into California. And that put us into a really stressed situation during a time of the day when we simply don't have enough capability to ride through those types of conditions.
Planned energy shutdowns were the only solution. The result was hours of blackouts for 2 days, affecting nearly 500,000 people. If California could have stored more of the solar power generated during the day to use in the evening, the crisis could have been averted. When solar panels produce more electricity than is being used by homes and businesses, the surplus energy can instead charge batteries. Then, when solar panels are generating less power than is needed, the batteries can discharge their electricity to the grid, making sure there's always enough for everyone. Since the blackouts, Elliott has been investing heavily in batteries, but that won't be enough.
Today, the primary battery storage resource on our grid are 4-hour lithium-ion batteries. And they are going to continue to grow in scale and scope here in California. But they are not going to be sufficient on their own to carry all of the load of the transformation.
The state's capacity has increased tenfold to 2.5 gigawatts. But Los Angeles alone uses 6.5 gigawatts. And lithium batteries can't provide power for long enough to get through the night.
We are going to need longer duration storage. You want a diversity of supply. You don't want to have such a dependence on a single technology.
California is ahead of the curve. But all over the world, renewable energy is growing fast. Without a revolution in energy storage, the world faces mass blackouts. Electricity grids need energy storage that is cheaper than fossil fuels to be competitive. They need them to be long-lasting to provide power for days or even weeks. They must also be fast-reacting to respond rapidly when the demand spikes. But above all, they need to store vast amounts of energy to help the world switch over to renewables. One nation that's attempting to build a giant energy storage system is Switzerland. The Alpine country boasts over 600 hydroelectric plants. But this know-how in capturing energy from water is being taken to the next level here at Limern Dam. to build a huge water-powered gravity battery known as a pumped storage plant. Deep inside the mountain, a turbine hall will connect Dam Liman to Lake Mut, 1.5 miles above sea level. A 2,000 feet difference in height between the two reservoirs will allow them to store energy. When there's surplus electricity available, the gravity battery can be charged by pumping vast amounts of water upstream to fill up the lake. The gravitational potential energy of the water in the upper lake can be released to generate electricity whenever it's needed. The pumps will then rotate in the opposite direction, acting as turbines, generating electricity and sending it to the grid. The engineers aim to generate enough electricity for the Liman Dam to supply up to 1 million Swiss homes at peak power. In January 2010, energy company Axpo started building one of the biggest batteries in the world. The project would be one of the most ambitious engineering feats ever attempted at such a high altitude. Overseeing the construction of this vast pumped storage plant was project manager Martin Hussler.
This was a huge work which has to be done with a maximum of 700 people here, and they work together. It was a huge construction site.
With no road access permitted to this protected part of the Alps, the engineers had to find a solution to lift all the necessary building equipment to the top of the mountain. So the team built 2 cable systems, each spanning just under a mile, that could lift the equipment at 10 miles per hour.
We had 2 aerial cableways. The first cableway has a capacity of 40 tons, and the second cableway has a capacity of 30 tons. And all the machinery was taken by the aerial cableways to the Lake Liman and to the Lake Mut.
Next, they had to dig through a wall of rock to the center of the mountain. Boring machines excavated a 2-mile-long access tunnel through which the team could bring the equipment from the top of the cableway. Then the team used explosives to excavate the caverns before collecting up the rubble to make concrete for the project.
The rocks were excavated from the caverns, were crushed and prepared for the concreting, because this was the main material for the concreting from the liner in the cavern.
The builders produced enough concrete to build 700 suburban homes, and even more concrete was needed for the dams.
Most of this crushed stone was transported with the aerial cableway to the Lake Mut and was used for concreting of the gravity dam.
This structure will be the longest in Switzerland, and it will triple the capacity of the lake.
The altitude of the dam is 2,500 meters approximately, and this is the highest in Europe. So this was also a logistical challenge.
The team had to excavate 2 main caverns out of solid rock. A powerhouse cavern for turbines and generators, and a second cavern to house the transformers. Then they had to line both caverns with concrete and build arches to reinforce the structure to withstand the weight of the mountain above them.
The whole plant, with all the tunnels, was approximately 400,000 cubic meters. And as a comparison, our main cavern is approximately 15% larger than the interior volume of the St. Paul's Cathedral in London.
The cavern was finally ready for the transformers to be installed, but there was an issue. They weighed over 200 tons, which was too heavy for the cableway. The solution was for the engineers to fit a funicular rail system into an access tunnel, which could lift up to 220 tons. Then the team built 4 pits for the turbine and generator units. These would weigh too much for even the funicular, so instead they meticulously assembled them in situ. First came the enormous pump turbines. As these blades rotate, they transform the kinetic energy of the water into rotational energy.
The runner has a power of 250 megawatts, and its design has 9 blades. And in pumping operation, the runner turns in this direction, and the flow goes through these channels and goes to the Lake Moot to store energy. This allows to fill Lake Moot in about 40 hours. In turbine mode, the water is coming from the Lake Moot, going through these channels, and the water flows through this channel out and is going to the Lake Limmen. And for all 4 runners, we have a total discharge of 160 cubic meters per second.
That's enough to fill 4 Olympic swimming pools every minute. Finally, the team assembled the generators, each weighing 360 tons. To generate power, operators open the valves and water flows into the turbines. The generators convert the rotational energy into electrical energy. The Linth-Lehman pumped storage site took 10 years to build, and it came online in 2020.
The feeling after we have successfully done the project was great, of course, because this is a huge project. It takes a long time to fulfill all these requirements, and we are still working on it.
It can now provide a massive 1 gigawatt of power on demand, the equivalent of a typical nuclear power plant.
It is very important to have this pump storage power plant because we are able to store a large amount of excess electrical energy produced by solar and wind power.
The Lehman Energy Storage Plant can provide Switzerland with green power even when the sun or wind drops. Pumped storage gravity batteries like this were first developed here in Switzerland in 1907. Today, they're the leading form of energy storage worldwide, with some of the biggest in the US and China. But they take a long time to build. So as renewable energy grows rapidly, other solutions will be vital.
Pump storage, it's near its limits now for several reasons. The main reason, of course, is that you need a convenient mountain, and convenient mountains usually don't exist anywhere near centres of population where storage is most needed. It also has other problems in that most pump storage systems are quite slow response. To get a lot of water flowing takes time. So some of the grid services which are needed demand something which can respond in under a second, for example, and certainly a pump storage system can never do that.
The supply and demand of electricity can change very suddenly, such as the power from a solar farm when a big cloud drifts overhead. So in order to keep the grid stable, engineers must build systems that can respond rapidly. Inventor Peter Frankel is a pioneer of renewable energy, creating novel wind turbines and the world's first commercial-scale tidal turbine. So he's well placed to understand the need to solve this problem.
I decided I'd like to get into energy storage, and I was looking around for some clever way of ideally using mechanical engineering of storing energy.
Peter was fascinated by the mechanism inside a grandfather clock in his home similar to this one, a family heirloom.
Basically, it has some very heavy weights, and those weights, under the influence of gravity, would like to fall down, but they can't because they're hanging from wires connected to the mechanism. So if I put the key in and wind the handle, this slowly raises the weights, and the energy from my muscles goes into the weight, and the weight then will be energized, basically, and ready to return the energy to the clock. This clock is 300 years old, and actually you could leave these weights for another 300 years if you did nothing else, and no energy would be lost. But if we start the clock, so the pendulum swings, now the clock has started to tick, and both the weights, in fact, will slowly descend. So, you know, it's an incredibly durable form of energy storage.
Peter's idea was to scale up the mechanism in a grandfather clock to store huge amounts of energy. To be a success, it would have to respond in under a second. To turn the concept into reality, Peter founded Gravitricity. He wanted to build energy storage units underground. Peter appointed engineer Miles Franklin to oversee the project in Scotland, as he had to self-isolate in London.
To store a lot of energy, you need either a lot of mass or a lot of height. So in order to get to very interesting levels of energy storage by lifting masses, it's good to go down. It's also then, once it's underground, it's hidden. So you can do it under a city, under a football pitch, wherever you liked, in order to store energy, and then without having problems with wind and weather and all these other things. And so we started to look at both existing mine shafts that are no longer being used for mining, and also the idea of sinking new shafts specifically for energy storage.
Before going underground, Miles was in charge of building a tower prototype to prove it could provide power rapidly. The team filled 2 steel containers with over 50 tons of high-density ballast. This would store energy when lifted up and release it when lowered down. The 30-foot tower was then lowered onto the containers and secured.
There was some, you know, scary moments along the way when we're moving very heavy things and lifting them, so there's a sigh of relief when they're all in place.
Once it was all assembled, they were ready to store energy for the first time.
We got to the moment we were going to lift the weights. We had quite a lot of the engineering team on site. So yeah, there was some tension.
They used power from the grid to raise the weights and charge the system with energy.
For that lift, it's the first time that the whole structure is supporting the weights. And you'd expect, you know, as you lift, some strange noises as the structure kind of finds its place. When the weight reaches the top of the tower, the system is fully charged. We can stop, we can pause, we can hold that energy for as long as we want.
But how fast can they return power to the grid when it's needed? Senior test engineer Jill McPherson knows how important that is.
Right now we're going through a transition from using fossil fuels towards using renewable energy to generate electricity, but that means that the grid is less stable. With conventional power, we have these big generators that provide a lot of stability to the grid, but with renewable energy devices, they don't really provide that. Sure, we wanted to be able to go from 0 to full exporting power within a second so that all the devices on the grid can operate safely.
All systems are go.
To generate back to the grid, the weight is lowered, the weight pulls down on the steel rope, which turns the winch, and then via the gearbox, turns the motor. The motor acts as a generator, so then we're putting power back into the electrical cable via the power electronics straight into the grid.
The tower had successfully generated electricity, but for the first few seconds, the power supply had fluctuated too much.
And so what we find is when we accelerate really quickly, the weight starts to bounce up and down, and that bouncing weight becomes a variation in the power. So what we need to do is find solutions to be able to accelerate really quickly, but then have that power output from our system quite smooth. So we need to try and find some way to fix that.
The team must find a solution to generate a smooth power supply more quickly when the weight starts to drop. Although the concept may seem simple, smoothly lowering a weight of 50 tons in a fraction of a second involves intricate mathematical modeling.
analyzing the dynamics of the weights and the movements and then designing them is actually quite complex. And so that was something that took us a while to get right.
1 month later, Miles and Jill have a plan.
We're testing.
After many simulations and tests,
It's clear.
they think they've figured it out.
Okay, so 3, 2, 1, go. If we want to go from 0 to full power, but have smooth power at the maximum power, then what we could do is apply a force that cancels out the tension oscillations in the cable, and then that corresponds to smoother power. Right.
To find out if it produced a useful source of power in under a second, they must analyze the results.
In this last set of tests that we just did, you can see that the power is much more smooth. It's a straight line, and that's what we're looking for. We went from 0 to full power in 0.96 seconds.
Gravitricity's prototype has proven it can respond rapidly to the demands of the grid, a significant improvement over pumped storage, which can take minutes. In July 2021, Peter Frankel was eventually able to make the long journey from London to Scotland to see the tower for the first time.
A bit better than a grandfather clock, yeah. It doesn't have such a nice face on the top of it, but yeah.
Now that this prototype has proven his theory, Peter has big plans for the next stage of his energy storage system.
In the near-term future, I think we're looking at, initially systems a few 500 meters deep and 6 meters diameter. So it's like a railway tunnel turned on it, vertically. We hope and expect that gravity-based energy storage of the kind that we're trying to develop could have a massive impact in terms of facilitating the wider use of intermittent renewables.
A typical system would store enough electricity to supply 13,000 homes for 2 hours. Gravitricity hoped to build their underground mechanical batteries all over the world to store green energy. Meanwhile, back in Switzerland, a startup called Energy Vault are building another type of gravity battery. The goal is to store energy as cheaply as possible. CEO Robert Picconi understood that the only way to move to 100% renewable power was to undercut the price of electricity generated by fossil fuels.
You have to be able to essentially compete with something that's about 5 to 6 cents a kilowatt hour. And the good news is solar and wind now is just a few cents, 1 to 2 cents a kilowatt hour. So the economics really work there. You therefore have to target storage that must be between 3 and 4 cents to have something that at least is on parity with fossil fuel, and therein lies the challenge.
To meet this challenge, the team came up with a specific design. The Energy Vault 1. A crane with 6 arms that could lift heavy bricks and stack them on top of each other to store energy. Then, to release that gravitational energy, the cranes lower the bricks back to the ground one by one. By building a tower made of thousands of heavy weights, they could store large amounts of energy and therefore bring down the cost. And by using mostly tried and tested machinery, they could build it quickly. But first, they had a thorny issue to tackle. So they built a quarter-scale system to try and find a solution. The problem is that when heavy objects are lifted by a crane, they can swing like a pendulum.
One of the main challenges we have in utilizing the system to move large objects is the environmental impacts on that object in movement. And it's a very important problem when you're moving large things like containers, for example, that are at the ports, and when the cranes are moving them, they will sway and impact the ability to precision place them. When we're moving around 35 metric ton bricks that we have to stack at height, it's very important that we be quite precise with that. And so that was one of the major challenges, was to solve for this pendulum effect.
When the trolley on the crane moves along the arm, the weight below starts to swing back and forth. making it almost impossible to precisely place the weight in its new position.
We had actually thought that the crane industry had solved this already for the movement of things in the ports and these large containers, but as we talked to other partners and suppliers in the space, it hadn't been solved, and so we had to develop the algorithm for that ourselves. And it's a very important algorithm because it's not only necessary for the precision placement of the brick, but also to deal with any unpredictable weather events, for example, a high gust of wind. So this was fundamental that we use software to solve this. So we took concrete barrels and utilized an existing crane that we modified to test the ability of software to cancel this pendulum effect.
As the test began, an AI control system could predict how the weight was about to sway. It then instantly adjusted the movement of the trolley to cancel it out with an equal and opposite motion.
One of the most fascinating things is to focus up on the trolley and to see the back and forth movement in light speed so that concrete barrels maintained that consistent velocity. And just amazing to see that software at work and manifest itself from the modeling to reality.
In January 2021, work began on building the full-size crane. But this would be nothing like the cranes you might see at a construction site. After laying extremely strong foundations, the team assembled and secured the 7 sections that made up the 660-foot-high tower. In the meantime, another team assembled the 3 rotating platforms called jibs.
Just one jib of the crane weighs 130 tons. So just to construct it is one thing, but then to maneuver it around the site, we had to use a special horizontally designed hovercraft system that could maneuver and shift from the shelter where it was constructed to a location where the crane then, the 600-ton crane, could be attached to that system and be able to lift that jib up so it can be constructed onto the crane itself at height. Just fascinating and amazing, and just a great job by the team to pull that off.
The crane stacked the jibs on swing bearings on top of each other so they could turn independently. Once in place, it was time to assemble the arms which support the transport trolleys.
Having enough arms of the crane with enough megawatt motors per arm, you could generate up to 5 megawatts of power and be able to essentially discharge that over a period of time, at least 6 hours, but ideally up to 8 to 12 hours, in a way that could be reliable.
While the multi-armed crane took shape, Rob faced a dilemma over how to make the 40-ton bricks in a way that was both cheap and environmentally friendly.
So normally, as you think about making any dense weight object, one of the easiest materials to use is concrete. The problem for us in concrete were many. It was too expensive. It was also bad for the environment. Concrete production still represents 7 to 8% of the greenhouse gases. So this, again, required more innovation for us to think about how to solve that problem.
They wondered if the solution might be a low-cost, plentiful material available at almost any site. Soil. So Energy Vault approached a specialist in building materials, Cemex, to develop and manufacture their bricks.
We had been working already on soil certification for some time. There are a lot of places where there are plans to develop network of roads, sometimes, very difficult places. And the easiest way we thought was, to be able to take just the soil there, dig it out, compact that material, and give it the ability to solidify.
To make the bricks, head of R&D, Davide Zampini, would need to adjust their process to make them even tougher.
These blocks have to be designed to last 25 years or more. The conditions that the blocks would be subjected to are highly variable. I mean, you can have, places where it's very hot, very cold, wind. These blocks are being lifted and put down, lifted and put down. So, they go through a lot of cycles of stress.
Cemex came up with a mixture of soil, water, a small amount of cement, and two crucial binding components. First, a chemical glue.
In terms of the strength, it has a lot to do with our chemical admixtures. Creates a strong binding element, what we call like the mineral glue of the block.
The second component is glass fibers.
Fibers are actually incorporated as a means to arrest any initiation of a crack that could take place. What we do with the fibers is make the material highly resistant to, especially when it's under tension.
Cemex are now investigating an alternative source of fiberglass that could be even more environmentally friendly.
Today we're looking at recycling the blades of windmills that create energy, so it's interesting now that the same element that is creating energy has to be obviously decommissioned, and we can recuperate the blades and process that material and actually incorporate it into the blocks.
This mixture is greener than concrete as it contains much less cement and avoids the pollution caused by heavy transportation. And crucially, it's also cheaper, which ultimately means a lower price for stored energy. But to make the bricks strong enough to be stacked 500 feet high, they needed one more step.
When you are paving a road, you use a roller compactor. And here, actually, we said, okay, we would use the same approach because, compaction is the best way to densify and make a material strong. But we needed to, process the material in a different way. And that means we had to, find a way to compress the material as much as we can, because the compression and the way the chemicals work further elevate the strength and the densification properties of the material, which are required to have the block survive those different conditions.
The pressure is applied by a custom-built machine with 40 powerful hydraulic pistons.
You need a compressive strength of almost 7,000 tons. If you think about the weight of a car that's about 1.5 tons, and you were to stack the amount of cars needed to generate 7,000 tons of force, that stack of cars would be as high as Mount Everest.
After 10 minutes of this immense pressure, the bricks are good to go. Once part of the system, each one will be capable of providing a megawatt of electricity while being lowered by the crane, enough to power over 2,000 homes. But before they stack the blocks into a tall tower, Rob needs to be sure it will be safe in all conditions.
One of the parameters in our design was to be able to build this at scale almost anywhere. But there are locations where there's a strong need for renewables that happen to coincide with some seismic activity, like in California. And because of that, we wanted to do another focus around research and science to deal with the occurrence of seismic events.
Energy Vault teamed up with Caltech and UC Berkeley to put the structure through its paces. After some small tests, they built a 1:20 scale model, 50 feet high, 7,000 bricks carefully stacked on top of the biggest shaker table in the US.
You can imagine the atmosphere in the room as we had the tower constructed and we're about to turn on the shaker table. A lot of anticipation.
The giant shaker table precisely simulated the 7.1 magnitude Ridgecrest earthquake that hit California in 2019.
As we got into the earthquake, what we saw is a vibrating of the system and a shuffling of these bricks, but the system never decoupled from the bottom and resulted in a full collapse of the system. Just this tremendous round of applause in the room because our software modeling and prediction was actually going to be correct. So as we reconstructed the tower, we did hit it with a larger earthquake, the Denali earthquake, which is up in Alaska, that was an 8.2 on the Richter scale.
Only a handful of locations around the world have experienced quakes as powerful as this. None in California have been stronger.
While we were hoping that maybe it might withstand that level of earthquake, it did collapse, pretty readily.
Nevertheless, the tests had proved the structure could withstand the vast majority of earthquakes, which many conventional structures couldn't do.
The implications for science and civil engineering of the fact that you could have a discontinuous structure not connected with standard mortar that could respond in a seismic event and shuffle and move and dissipate that heat and energy from a seismic event and therefore withstand better than existing structures was just a tremendous impact we felt like we were having also well beyond even our energy storage structure.
With the safety of the system beyond doubt, the team were ready to stack the bricks. The holes allow the cranes to lift the bricks securely.
Just amazing to see a 35 metric ton object coming off the ground and going at height 50, 60, 70 meters in the air. And not a new thing in terms of that amount of weight being lifted, but to have that done in an automated fashion and in a way that is going to be storing energy for the first time. So in this application, pretty cool to see.
Energy Vault expects to be able to generate electricity at a cost of just 6.5 cents per megawatt hour by 2025, making it much cheaper than batteries and competitive with fossil fuel. The EV1 could be perfect for storing energy in the day and giving it back throughout the night. But we also need a way to store green energy that can generate power for days or weeks if the sky turns gray or the wind stops blowing. Luckily, back across the English Channel, a company is engineering a new way to store energy that can provide power for longer periods. And instead of using gravity, they want to generate electricity from thin air.
I like to think of it as an energy storage system which is a bit like pumped hydro, which is physically a very, very large system, but you can put it anywhere you like.
Chief Technology Officer Gareth Brett has been developing the system at Highview Power for 12 years, working closely with Birmingham University in England.
What we're looking for is economic means of delivering energy storage over a longer period of time than the typical electrochemical batteries.
Lithium batteries typically provide electricity for up to 4 hours. Highview's goal is to store vast amounts of energy over a long period of time so they can then generate power continuously for days, weeks, or even months. To do this, they plan to store energy in the form of liquid air, which only takes up a small amount of space.
I've just put some regular air into this balloon. In this white pot down here, we've got some liquid nitrogen. It's at minus 196 degrees Celsius. We're going to dip the balloon in and it will get extremely cold. And the air in the balloon will now start refrigerating. And you can see the balloon is collapsing. That's because the air is getting colder, it occupies less volume, to the point where the air actually starts to turn into a liquid. So if we take that out, you can just see in the bottom, there's a little bit of liquid in the bottom of the balloon. It's about 7/100th of its original volume. As it warms up, it expands back into a gas. If we did what we've just done to the balloon, to all of the air in this entire lab here, it would shrink down to a volume of liquid only the size of this little oven, which gives you a sense of how much air you can store in tanks by keeping it as a refrigerated liquid.
When power is needed, the system expands the liquid back to normal air to generate electricity.
This rig demonstrates how we get electricity back out of liquid air. So the liquid air comes up the pipe here. You can tell that the pipe contains cryogenic fluid because it's frosted up. And down into this white tank, and in there is a bath of hot water surrounding a coil of stainless steel pipework, and it gets evaporated back into a gas.
As it warms, the liquid turns back to air, but at a very high pressure, as it can't yet expand in the pipes.
So at this point, we've got gaseous air coming back up this pipe, and that feeds up along this piece of pipework and down to our little air motor.
As the high-pressure air finally expands, the fast-moving gas drives a rotor to spin rapidly, which generates electricity.
So we're turning stored energy in the form of liquid air back into mains power that we're using to drive the fan.
In 2018, Gareth's team built a demonstration plant in Manchester, England, to prove the technology works on a commercial scale.
It was a system that could use off-the-shelf components from major industries like the industrial gas industry, which is where we get our refrigeration systems from to make the liquid air, tanks available from the construction industry, and turbines and generators that, of course, come from the utility sector.
At Highview's liquid air storage plant, air is cleaned up, compressed, and put inside a large industrial-scale refrigerator, where it is condensed into cryogenic fluid at -320 degrees Fahrenheit. The cryogenic fluid is then stored in large tanks, which can hold enough air to fill the Royal Albert Hall in London. To release power, the cryogenic fluid is pumped to a heater, where it evaporates back into a gas before driving a turbine generator to produce electricity. The idea works in principle, but there's a fundamental problem: the efficiency. Refrigerating the air so it's cold enough to liquidize takes a huge amount of energy, and turning the liquid back to gas takes a lot of power to warm it back up. This means most of the electricity is wasted in heating or refrigeration, and only 25% gets returned to the grid. But Gareth's team relished the challenge.
One of the things that we've always sought to do is to improve the efficiency of the system. We hit upon the bright idea of, wouldn't it be a nice environmental thing to do, is to not pollute the environment by dumping heat into it, but hold on to that heat and then use it later when we want to expand the compressed air, when we're generating electricity.
The heat generated by turning the air into liquid is stored and later reused to warm up the liquid air. But that's not all. The cold generated by evaporation is also stored and later used to chill the air that's being liquidized.
When we're expanding that gas, we capture some of the cold that the cryogenic fluid had, and we feed that back into the refrigerator to improve the efficiency of the refrigerator.
Highview claimed that recycling the heat and cold boosts the efficiency hugely, to 70%, and that the system has other benefits.
Highview, it's very kind to the environment. The working fluid is air. We take it, clean it up a little bit, store it for a while, then give it back. So no tailpipe emissions, no bad things used in its processing. It's about as good as it gets in terms of environmental footprint.
But the key to Highview's long-term storage and almost endless supply of power is their cryogenic liquid tanks. Javier Cavada is a board director.
These two columns that you see here, the white tanks, these are tanks that you find everywhere in the planet, in hospitals for liquid oxygen, in factories for liquid nitrogen, in houses, in industrial areas, totally commoditized.
The ready availability of these tanks means it's cheap and easy to add more for a longer-lasting store of energy.
If you want to add more duration, you just need to add more tanks, but you don't need to add a new charging station, a discharging station. The more energy you are storing, the lower cost you need to store that energy. The economies of scale of this technology are simply amazing.
Even seasonal storage of power is possible, where surplus solar energy in summer could be stored for use during the long, dark winter. Ultimately, electricity grids will need many different kinds of energy storage, depending on how much they need, how long they need it for, and how fast it must respond.
I'd like to see Highview really widely deployed, but alongside other long duration and shorter duration technologies. So, you know, I'm looking for the broad adoption of energy storage, but not just that. I'd like to see technologies advancing, so we've got new competing technologies coming through that are better performing, cheaper, and quicker to deploy.
As we develop our full-scale systems, we really believe that can become part of this energy system as it changes and allow us to kind of fulfill these big ambitions of decarbonizing our grids really quickly.
The energy transition is going to be massive over the next 30 years. Is going to be in the trillions of dollars, and therefore accelerating the need for the innovation to be able to deploy different technologies to reduce the greenhouse gases.
Make sure we can hit net zero in 2050. That is still a gigantic challenge, but the more systems like ours that we deploy, the better the opportunity we've got of hitting those targets. Let's hope we can turn what looks like a train wreck into something that looks like plain sailing.
By providing us with perpetual green power, these giant mechanical batteries could play a crucial role in saving the planet.